In today's video, we'll focus on moment of inertia. And so if you've read through the notes, you should be pretty comfortable with the moment of inertia of a point mass, namely I is equal to mr squared. And so in this video, we will focus on extended objects. And what we'll start with is a uniform density rod. Let's indicate that this way. So we have a thin rod with uniform density. We'll say that it has a total mass m and a length L. And specifically, we'll be interested in finding the moment of inertia straight through the center of the rod on a perpendicular axis as indicated. And so, of course, we cannot simply use I equals mr squared because r is poorly defined, right? The points closest to the axis have r equals 0, and the furthest point has r equals L over 2. And for that reason, we will break up our rod into point masses so that we can use the point mass formulation. And so I'll call this tiny point mass dm. And with that, we can say that di, the moment of inertia due to my point mass, is r squared dm. And of course, the way I would get the total moment of inertia is by adding up all of our di's. And since these are infinitesimal quantities, that means I'll be integrating my di's. So next, before we do any work, is we ask ourselves the question, does r vary with dm? Namely, is r different for different dm's? And of course, the answer is yes. R, in fact, will vary between 0 and L over 2, as we discussed. However, it's not obvious how we write r as a function of m. And for that reason, our goal will be to change dm into a spatial variable. And so how will we go ahead and do this? To do this, we'll introduce the notion of density. That is, we can say that lambda is equal to my linear mass density, dm mass by dl. Notice that this is very independent of this problem. This is just describing mass per arc length. But in this particular problem, we can make two more specific statements. First of all, because we are uniform density, I know that my density is my total mass over my total length. Secondly, I know that my arc length, my tiny increment of length, is aligned along the x-axis. And therefore, I can say this is the m by dx as opposed to the generic dl. So what have we accomplished? What I can now do is rewrite my dm in terms of a spatial variable. dm is equal to m over L dx. And so now let's see what that actually accomplishes for us, right? We can rewrite our integral. Oops. Our integral is now equal to integral m over L, which I'm pulling out as constants, r squared dx. And so now we can actually ask, well, how does r vary with x? And in this case, it's actually quite simple. If I set my x equals 0 to be at the axis of rotation, then r is in fact equal to x. We should be somewhat careful with that. If I am to the left of the axis, r is equal to negative x, because remember, r denotes distance from the axis of rotation. But for the purposes of this problem, no need to stress about it since we're dealing with r squared. So I'm going to replace r squared with x squared. And so this is our integral. Finally, our last step is to determine the bounds of integration. And here we have two choices. One option is to integrate from minus L over 2 to L over 2. The other is to use symmetry, integrate from 0 to L over 2, and multiply by 2, which I will go ahead and do. So we have 2m over L, x cubed over 3, evaluated from 0 to L over 2, which gives us 2m over L times L cubed over 3 times 8. And so finally, we end up with our answer, which is that our moment of inertia is 1/12 ml squared. So let's now consider the same rod. Only the one aspect that will change is that this time we'll have it revolve about its edge. So again, we have a rod of mass m, length L, but the axis of rotation is about the edge of the rod. And so it is a worthwhile exercise for you guys to go through the computation we just did, right? Set up I is equal to integral r squared dm. And in fact, we may as well quickly run through it, but I encourage you guys to go through the full steps. Our approach to density will be the same. Our density is m over L. And so we can rewrite our integral as r squared dx. The only big change is with our coordinate system. I will label this coordinate x equals 0, and I'll label the increasing direction for x to the left. And in that case, once again, r is equal to x, so that we have x squared dx. And the big change is that our bounds of integration are now from 0 up to L. And so going ahead and integrating gives us m over L times L cubed over 3, or 1/3 ml squared. So as we can see, the moment of inertia has increased from the previous problem, which hopefully makes sense. The average distance of our mass is much larger now that the axis of rotation is on the edge. But there is a shortcut, and that shortcut is parallel axis theorem, which you may have read about in your notes, but let's quickly run through it. And so the parallel axis theorem tells us that if we know the moment of inertia of an object about its center of mass, and we are interested in knowing the moment of inertia about some other axis, a distance h from the center of mass, then our moment of inertia is simply ICM plus mh squared. And so let's check this for this case. In this case, the distance between the edge moment of inertia and our center of mass moment of inertia is L over 2. In the previous problem, we found ICM to be 1/12. And therefore, we are doing 1/12 ml squared plus m L over 2 squared, which is 1/12 plus 1/4 ml squared, which indeed is 1/3 ml squared. And so let's leave off with one last rod problem. Only in this case, again, we'll be dealing with a rod of length L. Oops, that does not look like a rod. But in this case, I will say that our density is non-uniform. We will have a density. We'll indicate this edge of the rod as x equals 0. And our density will be linearly increasing. So density will be proportional to x, or I'll call it lambda equals alpha x. And so what will our moment of inertia be? Again, we're going to start with di equals r squared dm. And again, we're going to break up our rod into little dm's. But now, dm lambda is still equal to dm by dx, but it is equal to alpha x instead of m over L, since now our density is non-uniform. Okay, that's not a major issue. I'm going to rewrite my integral as r squared alpha x dx. And now, again, since we've already introduced our coordinate system, we have x equals 0. Our distance r is simply equal to x. And so our integral becomes the integral of alpha x cubed dx, evaluated from 0 to L. And I will leave the integration to you guys. So let's now move on and consider a problem that is two-dimensional. So this is a subset of a problem from the most recent AP exam, 2024. And what we're considering is a disk. The diagram does make things a little bit unclear, but we're considering rotation about this axis perpendicular to the page. And we're told that our density is a function of the radial distance to the axis of rotation. So non-uniform density, once again. And so in order to consider this problem, let's consider a quick subproblem first. Namely, let's consider what the moment of inertia of a uniform ring of mass m and radius r is about an axis through its center. And so again, we'll use that approach we've been using all along. dm is a tiny infinitesimal mass. We can indicate its distance from the axis of rotation. And again, we're going to be attempting to integrate di is equal to r squared dm. And so what we'll notice now is that this gets to be a rather complicated question if we just attempt to go for the integration. And that is, we would need to think about what our density is. Remember, the definition of linear mass density is dm by dl. But dl now is not an exact function of x and y. It is neither dx nor dy. And so there are ways of getting around this. If you are comfortable with polar coordinates, dl would simply be r d theta. But before we go down this whole long pathway, let's quickly ask a simple question. Does lowercase r vary with dm? Do different points along our ring have different distances from the axis of rotation? And the answer is no. They are all equal to capital R. And for that reason, we can pull it out from our integral. Finally, what is integral dm? Well, that is simply capital M, our total mass. And so the moment of inertia of a uniform ring is simply mr squared. Now, why did we do this digression? Let's return to our disk. So far, in finding all of our moments of inertia of extended objects, we've been breaking them down into point masses. Let's see what effect that would have if we use that approach for this problem. Well, we would have quite a number of point masses. And if you are familiar with this, in order to get the total moment of inertia, if we're adding up point masses, a single integral will just add up to a line. And so to get the total moment of inertia, we would have to evaluate a double integral. If this is confusing to you, no need to stress about it. We won't be doing that. Instead, what we've just realized is we know how to find the moment of inertia of a ring. And we also know that for a fixed distance from the axis of rotation, our density is uniform. And so therefore, I will break up my disks into rings. Now, since I'm breaking up my disk into an infinite number of rings, each of those rings has infinitesimal mass, which again, we will call dm. And as we've seen, the moment of inertia of a ring is mr squared. And so coincidentally, we are still using the formulation r squared dm for our individual infinitesimal moments of inertia. But the big change now is that our density is not a linear mass density, but rather a surface mass density. Now, traditionally, the symbol I would use for surface mass density is sigma, which you may see in a lot of readings or in textbooks if you read on this topic. For this AP problem, the density has been denoted rho of r. And let's pay attention to the units. Beta has units 4 kilograms per meter cubed. R has units meters. So notice that this is a surface mass density. It is units of kilograms per meter squared. And so what I will now say is that rho is dm by dA, and this is equal to beta r. And so I can now go ahead immediately and rewrite my integral as the integral of beta r cubed. Rewriting dm is beta r dA, so we have beta r cubed dA. Again, we're not quite done. We need to come up with an expression relating dA to something spatial. In the previous problems, this was directly accomplished by our density step, but now we do have a little bit more work to do. Notice that my rings each have thickness, infinitesimal thickness, dr. But as I go along to larger radius, while my area remains infinitesimal, right, it is proportionally larger if we have the same infinitesimal thickness. And so let's think about what dA will be. An easy way to think about this is to imagine unfurling one of our very thin rings. Obviously, we'll have some curling at the edges, but that is negligible. We'll have thickness dr and length 2 pi r. And so this tells us that dA is 2 pi r dr. And so going ahead and plugging that into our integral, we'll have the integral bring out the 2 pi and the beta r to the fourth dr. And our bounds of integration will be from 0 to 0.3. And I will leave it to you to complete this calculation.